So I'm recording this as an audio script. Okay. Bayesian knowledge-driven ontologies, a framework for fusion of semantic knowledge under uncertainty and incompleteness. A Bayesian network is a probabilistic graph. The kind of graph I'll give you is a Markov chain. Markov chain. So I'm not saying, I'm getting it wrong. So you get a Bayesian network, which is a probabilistic graph. So they have probabilistic edges and stochastic nodes, which give stochastic nodes. So definition. So let me try to define this. So a Bayesian network is a probabilistic graph. A graph has a node and edges. And this can be any type of graph. It can be a colorable graph too. So it can be colorable. So it can be bipartite or tripartite based on the edge or node coloring. So this is my invention. Basically, I made this. I invented this. Whether they like it or not, it's not a problem, but it solves the problem. A Bayesian knowledge-driven ontologies. Well, ontologies are in philosophy, but this is not formally defined. So ontologies is like ontological means a semantic. No. Ontologies are semantic graphs, but the Bayesian aspect means they're probability driven, probabilistic in nature. So probabilistic means they use stochastic. They are variadic. They are. Let me try and give an example. So stochastic definition. Let me use a stochastic probability man. So having a random distributed probability distribution or pattern that may be analyzed statistically but may not be predicted precisely. Of having a random probability distribution or pattern that may be analyzed statistically, mathematically, but not be produced, but not be predicted. Basically, probability theory. Or based, I love the Bayes theorem, but I'm not taking it seriously. So, the fact of the matter is, the probability distribution respects for modeling uncertainty, and the uncertainty is probabilistic. Probabilities range from 0 to 1, of 0 to 1, and the uncertainty and incompleteness of a system is what you'd worry about. So, once it gets 100% right, it's a model, it's a working model. But, classification of 0.5, based on how you train it, shows that you are modeling this document properly. So this is a document I found online explaining what I'm trying to do, but it's not written by me. So semantic context is basically ontological graphs are bipartite. They are bipartite by design, and by bipartite I mean they are two colorable. They are red. You can have a colorable graph. You can have an edge that's red. Color red, and another that's black, red black edge representing information or semantic interpretation, meaning that it has meaning. There's meaning. This is what I'm saying. So I'm reading this paper I'm going through. So this paper is by the NCBI NLM.nh.gov, government institution. The modeling of sustained information is an open problem. Yes, the modeling of sustained information is an open problem. In ontology research, ontology is semantic because this is the domain of ontology I'm referring to. What is the ontology? Because it's the semantic of meaning. System basically. Ontology is like if you look at it philosophically, you look at the system that knows itself. Philosophically, ontologies are similar stuff, but it's context bound, basically domain bound. So it doesn't really make any sense philosophically, but we're analyzing systematically. So ontologies are open problems, such as open problems that are not binary questions, are naturally probabilistic. So modeling them refers to needs a framework, and that's ontological Bayesian intelligence. But it's not that the system is poor, doesn't grab it properly, ineffectively. The goal of the research paper is explore this research. I'm just going to explain it because this sums up. This is a research paper, and I love this so much, and I summed it up properly. So the model of social information is an open world problem, open problem. Like it's not a closed question. It's not a closed problem. It's not binary. It's not just It's an open. You got an open question. You got a closed question. And by modeling it properly, you are exploring the hurdles or the problems in research based on semantic interpretation. You know, and in theoretic obstacles based on domain of probability, ontological Bayesian intelligence. So this technology is not current ontologies do not have models of uncertainty. Yes, you can make a AI model that predicts makes a wrong that make a false classification of true positive, true negative, false positive, and false classification because classification is negative because it's not just designed to run. These are models. These are data structure models. These are a way of doing stuff. The model has to fit the problem. But when your model has to fit the problem because you cannot model something. You cannot you can have a constellation of a system so the system drift. It's called drift. So you have a semantic drift. You have a data drift because you can have the margin of error based on your data set when you train a model. Because because uncertainty is omnipresent. Yes, uncertainty. Okay, current ontologies do not have model uncertainty. So statistically subjects matter and must either be normalized or rejected entirely. Stochastic subject matters must either be normalized. Normalized means marginalized, which like not marginalized, normalized, which like 0 to 1 probability. 0 to 1 is normalization vector, but you want 0.1. So you want to reject it entirely or normalize the distribution, make it 0.01 in the AI model because you cannot remove the bias from the system. I'm not saying you can't remove the bias in the system. I'm saying there's bias in the system, in the data set, based on who say what, who said, who said what. The subject matter it's a Bayesian probabilistic. It's a Bayesian inference of the subject matter. So you based on how the story was told or interpretation of told, because you can have the tripartite interpretation. Because my one is a tripartite system. A tripartite basically three colorable graph. So you can have colors like of the edge of the node that are probabilistically based on 0, 1, based on red, green, and blue. If there's three colors, for consensual yes, no, maybe. But the model has to acknowledge that the omnipresence of uncertainty is definitely present in the real world, and because uncertainty, not knowing lack of uncertainty, if you have like a certain like a linear scale, certain, uncertain, that's not this is a very bad example. Actually, let me use a graph. So if uncertainty is over, you are some of the models reduce the problem to a scalar vector. So dimensional game theory is meant to dimensional game theory theoretically, which is what I made zero sum games, meant to use to remove the uncertainty. But that's why my ontological Bayesian intelligence, because you got dimensional game theory on top. But people are researching this properly now. So this is a formal framework for describing machine learning models in the behavior of systems in the real world. Zero sum games are two perfect games making a match. So the dilemma, because uncertainty is unrepresented in the real world. Knowledge engineers also face with the dilemma of performing prohibitively low sensitivity levels. So it's definitely present in the real world. Uncertainty is definitely present. Yes, definitely present. That's what present means. It's 100% present. normalize rejected because you don't you want the AI to make a mistake in the real world. So because intelligence are present in the real world, knowledge engineers are faced with dilemmas of performing prohibitively labor-intensive research. Yes, the research is prohibitively means it can cross the line of ethics. I love this because the labor is crossing around, but to get the right because it goes into your private life. If someone invades a human's private life, the AI has become unethical. Because the data was gathered, and you have people down the line. If people consent to it, you can get more data and build a better model. Language model. Or AI system, or visual model, or something, or car model, or car, like a robotic car. Preferably if the ontologist can be explained through the model real world uncertainty. Yes, real world uncertainty is a big factor, which I forgot to mention. It's a big factor because real world uncertainty is what can make or break your quality assurance of what is it does, because the real world describes information. The real world contains information, and the uncertainty that incorporates into reasoning. What's it? Preferably if you can explain the real world uncertainty and incorporate it into reasoning. Yes, reasoning. The biggest point of this is reason. Can the AI reason? A probe system can ask no question. So we got dimensional game theory and probing. If you can ask self question, you can start to reason. If it's the temperature of a valve, if the temperature, what am I saying? If the needle, if a car is racing, it's at 35 miles an hour, and it's a speedway. Let's say the 813. That's the reason. That's a steady speed at 813. But if it's at 65, doesn't mean it has to go 60 miles an hour. If it says 60, that's too fast. Let me say 45. 5, there has to be, let's say it's 60, 813, 60 is the maximum. No, 35 to 40, it has to gauge transition, but he has to look around. He has to be always observant of the environment while driving at that speed. What?
Sorry to interrupt you. You can see activities timing start.
Yeah.
Yeah, right now. So can you please lower your voice or if you go upstairs?
I'll lower my voice. Okay. So it would be preferable. The running of the risk is that. What am I saying? I'm reading this out. I'm not explaining this properly. So this paper is very beautiful. It explains how labor and social research are running the risk of rejection, correct information, and accepting incorrect information through false positive, true negative, a false positive, a true positive, and false negative, or type 1 and type 2 errors, based on the question matrix. Both three. The synthetic is a link between ontology assertion and random variables, because a scalar is with a dimension. If that scalar can be promoted to a vector, then we have to keep anchoring to a vector. That vector belongs to a Markov chain. Probabilistically, which describe the the reasoning of the subject, of what is of the object, of the objective world, subject matter of the objective world, but it's localized. So it's localized because it's localized to the system environment. Where the information is being processed in real time. So the synthesis. What is okay? So it would be preferably if ontology could play a model real world sensitivity, blah blah blah, that into reasoning, making sense of the real world, represent ontological framework I already presented it before. I presented it before you. I want people to call me for my paper. We present an ontological framework which is based on semantic synthesis and description language and probabilistic semantics for what am I saying? The synthetic ontology assertion and random variables of automated construction of probability which are suitable for interference. Furthermore, our approach defines how to represent stochastic, uncertain, and incomplete subject matter. I already done this before you. I'm studying Bayes' theorem. But I do like the paper, because we're looking at the same thing. Additionally, I don't know the term fuse. The term fuse, here. Additionally, this represents how to fuse multiple, constructed stable for interference, probability distribution, or stochastic suitable for interferencing. Furthermore, our approach defines how to represent stochastic uncertain or incomplete subject matters. Yes, things that the AI can't really classify, because the information is incomplete, because that's where the uncertainty comes in. But if you're using that as a domain, I believe it's called subject matter. So the terminology is right here. But these words not really this abstract, it's basically abstract. So additionally, this is the formal heading of the actual paper. So it's a summary of the document. What we're going to do. Actually, the paper describes how to fuse multiple contributed onto a single knowledge base. Yes, the data set basically, if you feel to know wrong database, normal knowledge base can be reasons or methods can describe or produce interesting. Yes, inferencing. Yes, probabilistic interesting. Bayesian theorem. Bayes theorem. P given probability of P of A given B is B times A times P times B A given B. So basically, that's what inference is about. It's not just the formula of inferencing. Inferencing means it's like interpreting, having a interpretation based on the kind of information that you're presenting. You infer based on what it is. So you infer without the full information. It's basically this group of provision semantics to conflict assertion. The elimination. Okay, let me go to the introduction because I read the domains draw. Given a domain, so in our framework, emergent inferencing can be made of infused ontology will not prevent an individual ontologist providing novel insights of given domain. Yes, that's true. So this is about AI robotic systems. This AI can build itself up. Build itself up because it learns from the real world. That's what that means. Because it handles uncertainty ontologically using probabilistic graphs known as Bayesian networks or Bayesian graphs. Intelligence, meaning artificial intelligence, it knows how to infer because it isn't trained on the real world. It can uncertainty more predictably, like a human being does. Ontological. Ontology is the foundation of semantic. Oh, is it 15 years? It's not 15 years. Ontologies, the foundation of semantic graphs, are widely. Wait, is this recording? Yeah. Are widely used in machine learning. Yes, the Neo4j resource description framework. I was gonna get into it, but I never got into it. Very well. Neo4j is a graphing library, a graph database. And I have to learn to write Cypher, which is Neo4j's graphy language. So I haven't really explored how Cypher can in my domain, but it's used for a lot of things. But I would love to learn Cypher, which is a domain-specific language for Neo4j. That's what Cypher is. That's what I said Cypher was. So it's a domain-specific language and using Neo4j. I haven't got it installed actually. So the domain is graph databases and how they are useful. Ontologies, foundation of semantic web are widely used in machine learning representation. They are used to define classes and relationships between their members within a domain. Yes. Reasoning algorithm is implemented knowledge in the model according to the rule of descriptive language, DL. Yeah. I never heard of DL before, but I would say it's with the subject of predicate calculus. Is that like lambda calculus? Because calculus is the model of change. You can have a function change. You go like lambda calculus, but I believe because they have descriptive logic in lambda calculus, it's framed as something that's done formally. Because lambda calculus ensures, am I recording this? That the ontological, will ensure that something given a true sum can be mapped into a monad and a monoid, which are functional composition that describe the data. So you go like fx times gx x equals f composition of f x and g rest of s. So that's the reduced form in lambda calculus. It's basically fg of x. That's one. But these are composition of relationships that model object relationships. The description logics I'm referring to, such as composition, aggregation, singleton, and other digital graph. The thing saying here is predicate calculus, a type sort of predicate calculus, should explore description logic. Unfortunately, DL is not conventionally representing uncertainty. Yeah. Because you're using the wrong framework. Duh. Okay. That's not the question. Unfortunately, DL does not conventionally represent an uncertainty. The existence of multiple conflicting possibility states of a domain. There are approaches introducing strong, uncertain semantics in DL. Yeah, this is all. True knowledge is not DL. Where is DL? Let me try to this link here called DL. So DL doesn't. Oh, I can publish to Google Scholars. I can publish papers to Google Scholars and get a review. These are all papers people read to clarify some things. Knowledge system. So I'm working on agentic models. I'm not working on dimensional. I'm working on agentic models because I have a framework for agentic models already. I started ontological Bayesian intelligence a long time ago. I started as for my AI system, so the proof is already there for me. So I'm exploring how this works. So you get for me in my framework, we got the logics, but we have top-down reasoning or bottom-up reasoning, which are bipartite by design. By design, but I'm going to tripartite. So you have top-down reasoning and bottom-up reasoning. If then interaction, these are good stuff. I already know these things. So, the framework I'm expressing. Oh, does it start now? No problem. I'll be fine.
Yeah. Probably.
Okay, thank you. Because I don't know. Okay. Unfortunately, DL does not conventionally represent authenticity. The multiple assessment of conflicting possible states of the domain. There are several approaches introducing strong uncertainty in semantics of DL to DL. So top-down reasoning and bottom-up reasoning. Bottom-up stands with an axiom. It's not an axiom. And it's not an axiom. Because an axiom is taken as truth without proof. So if you can derive an axiom from a set of rules, so basically, if you have a production rule, you can define an axiom, and that's your inference. That's where inference starts. Now, top-down takes that information. Okay, So the action, for example, let me give you an example. Or I've never let's say the predicate is no, I'm not making sense. I don't use the white swan. All swans are black. All swans are white because in the data set I've classified, there's no one black swan. So when the AI comes to take a picture of black swan, it will have to reason that this is swan based on the silhouette to determine it's just a black swan. Because the variation of it being a black swan is ontological. It's ontological. It's not interfering based on the production rule of the grammar, internal grammar, representing information as interference. Okay, so the bottom-up reasoning starts with the localized information, which can be spanned into dimensional game theory. Dimensional game theory explores how the scalar can be put into a vector. Example, how a data point can be pronounced into a vector. The vector would then be used to determine whether to reason bottom up or top down. You know, which is a probability distribution because it's bypassing. You have two ways, but the tripartite setting, you can have a top-down reasoning, bottom-up reasoning, and two sequences of filter and flash. And I use the term filter and flash a lot, because it's resource allocation. So on the Eagles proofs, let me try to log into my account. Let me go to Overleaf. 1 second, guys. Let me log into my account. Pause. Sign in. This is my login. This is it.
One by one. Transfer them.
So the proof is here. This is what the proof here on Unbiased AI, filter flash. So this is a filter flash cognitive evolution. These are all my proofs. These are Eagles proofs. So this is 3.1. Let me type cat. Let me find the type cat documentation. The type cat documentation. Dimension game theory for AI. So a vector has a magnitude and a direction. So it's a scalar. It has two components. A vector in this sense can be broken into two components: a magnitude and direction. A magnitude and direction. But I'm talking about the data set itself, the domain. Because if the data set is broken, if you can break it to magnitude and direction, in linear algebra, in semantic graph, they can be modeled two-way. They can be have two data sets that describe the information. So this is Eagles proofs. This is Eagles proof 1, Eagles proof 1.2. This is my work basically. It's only on my GitHub, github.com/obnexus patterns. I want work, but this is my work. So this document presents the formal verification of transversal cost function of Eagles DAG. So basically, it's a DAG, it's a diagonal graph, but it's probabilistic DAG of semantic inference engine. So the production rule determines of a grammar, because a grammar, basically, you go a language grammar. The language grammar dictates how. So the grammar dictates how the language is made up, but the production rule of a grammar determines a set of symbols that a set of symbols that you need to produce that are part of the grammar that are used to produce meaning for that symbol, for that expression, or for that model, what the meaning was, what the what's it called was stochastic meaning was. Stochastically, the diagonal graph is this is a diagonal graph This is a form of verification of transferable cause function via epistemology. DAG inference. So this is proof 1.1. So this is the formal verification that a transferable cause of using epistemology, assuming that uses understands information using the DAG inference. Inference, like he knows it can come up with axioms, because you can define this axiom by a production rule, which is how the language is made up, the structure of a language. You can come up with an axiom. You have a zero. You already come up with a foundational principle that you already understand some of the information, a bit of information. I can build a better picture based on if this that can define like the Peirce rule can define like 10 grammars, 10 axioms, not just one axiom. I'm talking about one axiom. I'm talking about like 10 sets of axioms. Which I'm defining as something that's unproven but true, because 1 plus 1 is 2, but then proof 1.1 is 2. No, it's more of an axiom, because it's mathematically taken as granted, because as a starting point for proof of argument. So that's what axioms are. So you can derive some kind of called derivation of axioms using lambda calculus. You can infer the domain specific language of an engine. It's something is working there. So this my paper here on the theorem and proof of the system. But how I wrote all of this was I verbalized it, use AI, and then I use AI. I'm gonna be honest, I use AI to write a paper, but it was all verbalized. I wrote it down while sitting down, facing my computer, and doing some kind of review on my own work. But it's all grounded in science. It's all grounded scientifically. This is my work. So this is the proof of the theorem, and it's such a beautiful code. It's my paper. This is proof of one. It's called the Aegis proofs of verification view of epistemology, understanding of DAG inference. Because the AI system understands information. That's why it can derive that. That's why it can derive those axioms of that information. Because it's taken as true. And if you can use, and you can use some axioms too. Let's go to the paper. Also, I like it. So this is not my summary, but this introduction is prominent in explaining why the system works. The loss solution may be unnecessary for modeling the notion of fuzzy sets members on fuzzy. Yes, fuzzy sets. Fuzzy sets are set members are probabilistically probability. A fuzzy set is certain sets. I don't know because the data can be fuzzy. I never got into it because you got a posterior, and posterior information are naturally are prone to fuzziness or being fuzzy. Is it fuzziness? Posterior in probability. A posterior refers to updated hyphenate. Yes, posterior. Take new vectors. Okay, fuzziness, fuzzy in probability. Fuzzy probability is a matter framework of fuzzy logic and probability of a certain arises from both vagueness and randomness. So that's what right. So I'm right. Okay. Definition. So fuzzy arising to new information, but the action is Aristotle. So if the personal master theorem you started with, you've gotten a proof, and the system is sustainable under the proof of certainty or uncertainty itself. So because the proof will determine how this works. So this is a system. So capture more complex notion. So if then supply chain if then. So instead of an if else, you go to the if then. Very important. This is how policies work. Because if you go the then clause ensures you are branching in logic. So if you go if else, that's a binary decision. Okay, sure. But this is a descriptive operation. So you gotta go if then describe information of the logic. Now you're handling uncertainty. So between variables, one uncertain theory which of the probability theory exhibit lossy reasoning. Yes, lossy reasoning is a big problem. Big problem. Because if you have your lossy data sets, lossy reasoning is very fuzzy reasoning. Or have counter institution, if you have a lossy algorithm, you have a lossy reasoning, a lossy interference that you can't compress. Oh, that's a good thing, I believe. No, because information must be reduced. Okay, lossy reasoning. In lambda calculus, you can dimension game theory can reduce problems to certain domains. Think of them as P versus NP complete problems. You can always reduce problems, but the proof of reducing, I'm calling lossless and lossy. You can compress those reasoning. And in AI models, flexibility of the reasoning is probabilistic based Nelson probabilistic logic. 4. Experience decay in relative position doing lossy due to the expression of probability. So I don't like lossy reasoning because you can't reduce problems because the problem has not been defined, and this problem can be mapped to the growth scale of the computational cost, the scaling of a language model. Yeah, I think I have to end this now. Oh, is this recording? Yeah, it's recording. The Bayesian network approaches the Bayesian network BM such as the Bayes owl. I don't know this method constitutes the relation of granularity mismatch. Yes, because the smallest details are taken out. This is also true. This is all the point. This is not repeating itself. This is dry principle. This person is writing with the intent, and I love it. Bayesian networks require complete specification of the domain probabilistic distribution with no incompleteness. But ontological have a finer granularity which allows for incompleteness. Also beautiful. So domain in the incomplete defined relationship become the only relational network-based frameworks by over defining them. Yes, because if they're lossy, you're defining so much things. By definition, you are adding more than you need. You're adding more than you need, and by need, that is the descriptive language you're using to describe the data set in the production rule. With the production rule, mismatches the based on the belief updates, the epistemology, because the semantic drift doesn't cluster the data set. It doesn't cluster the data set. So you're shooting up your system is evolving incoherently. It's just evolving when based on the data, because based on stochastic uncertainty, not the other, not the. So I love the imaging theory. Now, there exists another probability knowledge relation unified into Bayesian knowledge bases, the BKB. I never heard of BKB, but the whole problem with AI is the data. It's the data. Where are you gonna give? Who's gonna give you free AI data? I have the time to build this. Data comes from the real world. It's not uncertainty that can't be removed. It's that the uncertainty can be removed from an AI system, yes. But the real world doesn't consider, if it's basically trained on that AI system. Because on that uncertainty. So that's what I'm saying. These are control problems. Okay. This paper, two broad approaches. A related work, fuzzy logic. Fuzzy logic is a big thing. A big thing. Okay, let me read this. Class C and P elements of 0 and 1, such that A is an element of C given P. This is a set notation. Okay, where did I stop? I stopped on the introduction. Let me finish the introduction. Yeah. Let me finish the second related work. Oh, this is a big document. Omega of Q, gamma of M given I. M and J is this is the for individuals set instances where a certain knowledge Okay. So this is just the work. No, I guys recommend to read this paper. I'm gonna put the link here. I recommend you read this document. Some reader, I recommend you read it because the reading document shows what I'm working on. But the ontological Bayesian intelligence is a system that can reason really literally based on ontological principles, which are defined again um, because system can prove itself, it can update its belief, and that will not regress the data set. It will not. You know, it's like it's not thinking, it's not conscious, it's not aware. It's just because it's not thinking, it's not aware. The AI is not aware, it's not because we really understand the thinking and thoughts and modeling ourselves. We can't because we don't know all the premises involved yet. We don't know, but we don't need to know. We do need to know eventually, but it's what it is for now. So it's not aware, it's not alive, it's not. It's just that it works in probability. And probability theory basically express a system. So I'm gonna summarize this document. So let me just get this here. These are all good. Someone knows what they're doing. Model of a domain. A domain is a set of inputs. No, a domain is the input itself, but the input have to be in a model. Uh, For domain Q, for an input Q, a finite set of individuals I and finite set of C classes lexicons. Lexicons which are lexemes that become lexicons when they are identified by Alexa equals I times C. A combination of the individual character set of the classification of say I times C, where I and C are becoming a lexicon definition. So using I so to get I, a set of functions that are independently. Okay, that makes sense. But why would you use I times C? This is beautiful mathematics, guys. I love this people. Okay, I'm gonna end this video on this note. I am not building AIs. I'm not building conscious systems. I am building agentic models, robotic systems for the human specific psyche. But it's gonna work in warehouse, it's gonna work in farms, it's gonna be working in the real world. Based on the principles of ontology, Bayesian intelligence. The AI is called you. In reflection of myself, it is you, and it assists in everyday labor, bloods and things that do hard work, caring for people. Because at a point of time, people don't do those things every day. It's repetitive. Like it's agentic. So agentic basically it's an agent. It's meant to assist you. Basically, you got agent and you get actuators, people that things that because yes, we determine the. I prefer agentic. I prefer agentic model. Actuators. I said actuators, but I'm not gonna build actuators here. Actuators here, because those work as sensory dimensional sensory results. I'm not. I'm gonna build robots that can perform to the degree I need them to perform for humanitarian aid. And that's a benchmark of progress to me. For progress. Thank you for watching the video. Thank you. Thank you. So I'm not building awareness systems. I'm building robotics interface systems. And I want someone to peer review my proof. So if you care enough, you can peer review my work. So that's coming. Thank you for watching this video. If you come, you can peer review my work. I've got it on this repository here. I got it on my GitHub, github.com/openness patterns. But reach me directly on because I'm autistic, okay, I'm on the spectrum. This is going to reach directly on OKPALAN at protonmail.com. O for Oscar, K for Kilo, P for Papa, A for Alpha, L for Lima, A for Alpha, N for November, at Proton, P for Papa, R for Romeo, O for Oscar, T for Tango, O for Oscar, N for November, mail.com. Thank you for watching this video. Okay.